Okay, let's talk about simplifying radicals. Now, a radical in math is just a fancy way of saying a root, like a square root. And it's this symbol right here called the radical symbol, or radical sign. And what's inside it is called the radicand. But basically, if there's no number, if it just looks like this, then that's a square root. So if a squared equals b, then a is the square root of b. Okay, now if there's some common square roots over here in this table, probably familiar with most of them, but some not, and that's okay. So you can always check this table. Now if you have exponents, like on a variable, you just divide those by 2 to get the square root. For example, the square root of x to the 4th would be x squared. And that's because when you multiply powers, you add the exponents. So the square root of x to the 4th is x squared, because x squared times x squared equals x to the 4th. And the last thing to mention here is that the square root of -1 equals I, the imaginary number. And it is imaginary because if you think about squaring a number, like let's say we have 3 squared, that equals 9. Well, if you do -3 squared, that also equals positive 9. And so when you take the square root of a number, it always needs to be positive, because there's no way you can get a negative by squaring something. Because if it's positive, well, that's going to be positive. But if it's negative, a negative times a negative is also a positive. So we've come up with a way in math to allow for this, and that's with imaginary numbers. So if you have the square root of a -1 or a negative anything, you're going to have an I in your answer. And you'll see that when we do some of these examples. So let's get to it. Square root of 100, really simple. That is 10, because 10 times 10 is 100. Square root of 49, that's 7. Because 7 times 7 is 49. All right, we have 121y squared. So first I would suggest doing this piece by piece. So the square root of 121, if you're not sure, you can check the table. It's right here. That is 11. Now the square root of y squared, just divide that exponent by 2. So that would be y to the first power, or just y. So 11y is what we want here. And if you think about it, if you multiply 11y times itself, you do get 121y squared. Same thing with number 4, just go piece by piece. So 16, that is 4. 4 times 4 is 16. And then just divide these exponents by 2. So we get x to the first, y to the second. Here's our first negative. So this negative inside the radical, this is where we get an I. So the square root of 36 is 6. The square root of -1 is I. So this needs to be 6i. For number 6, this negative is outside the radical. All right, so we don't use it when we take the square root. We put it on after. So the square root of 9 is 3, and this negative makes that a -3 because it is outside the radical. Okay, number 7. We have 3 square root -16. So first take the square root of -16. The 16 gives us 4. The negative gives us I. And this 3 is being multiplied by this radical. So we have 3 times 4i. Well, that's just 12i. That's the way that works. Number 8. 2 square root of -25x to the 6th. All right, so same idea as number 7. We take the square root of 5, or 25 is 5. X to the 6th is x to the 3rd. The negative gives us an I. And this is all being multiplied by that 2. So it's just 10x to the 3rd I. Now, here's what happens when you have remainders, and you'll see what I mean about that. So, up till now, all the things we've taken the square root of have been perfect squares. They have a whole number square root. And you'll see sometimes that doesn't happen. First, let's do example 9. This is pretty simple. A squared, b to the 5th. Those are both even numbers. We can divide those by 2. Let's look at number 10, though. Here we have 27, which is not a perfect square. 27 doesn't have a whole number square root, like 9 or 16 or 25. If you try to take the square root of 27, you'll get a decimal. So what we have to do is think, is there a perfect square factor of 27 that we can take the square root of? So if we think of 27 as 9 times 3, 9 is a perfect square that we can take the square root of. And then we still have x to the 6th, y to the 12th. So let's evaluate that. The square root of 9 is 3. The square root of x to the 6th is x to the 3rd. The square root of y to the 12th is y to the 6th. And this 3, you can't take the square root of 3 and get a whole number, so we're going to leave it inside the radical like this. And this is the exact answer. We could estimate, get a decimal. The decimal would be, it would go on forever and not repeat, so we'd have to round and it wouldn't be exact. This is the exact answer, so this is how you want to write your answer here. Don't get a decimal, just leave any leftovers inside the radical. For number 11, much the same. We have 8. 8 is not a perfect square, but it does have a perfect square factor, which is 4. Similarly, x to the 7th, that's not an even number, so we can't just divide it by 2 or we get a decimal. So we have to kind of split it up into x to the 6th times x. Just take one of them off. And then we have y to the 8th, z to the 6th. So if we evaluate this, just take the square root of what you can. The 4 gives us a 2. X to the 6th gives us x to the 3rd. Y to the 8th gives y to the 4th. Z to the 6th is z to the 3rd. The negative sign gives us an I. And then what's left over is a 2 and an x. So in the radical, we still have 2x. And that's as much as we can do on that problem. It can be tricky to find the largest perfect square factor of a number, but if you just divide by perfect squares like 4, 9, 25, 16, 36, those can kind of give you what you need. All right, 12 is 45. Again, if I'm not sure I can divide, 45 doesn't divide by 4, but it does divide by 9. It's 9 times 5. And so the square root of 9 is 3. The 5 has to stay in the radical. So if you have non-perfect squares, just take the square root of the portion of that number that you're able to.